No camera, no microphone, but that's all right. Uh, um, all right. Good morning, everybody. It is sure enough. Uh, that's what I get for poking fun. Um, I hope you heal up. It is April 20th, and we've got a couple of guest speakers this week. I wanted to wrap up somewhat this discussion about statistics and statistical measures and the mathematical measures. So I've just got a couple of things this week in that vein. I've got Dr. Brian Aguiar coming in today at 10 to piggyback on my bivariate analysis presentation, where I kind of told you about how you would visualize the change in mean or the correlation between categorical variables. He teaches this stuff more frequently than I do, so he's going to piggyback on that, and we'll kind of somewhat close the book on statistical measures, really. Um, and then uh, just recently, my colleague, Dr. Worley at the University of Central Arkansas math department, um, told me that she could do a Q&A. So she's a statistician, R programmer, and she has all of this stuff just fluently, just right at the tip of her brain. So she'll be in at 9 o'clock on Thursday this week to go over and fill in any holes that you guys might have had. So I'm hoping that everyone will have at least one question that they'd be willing to ask, because there's nothing more embarrassing for somebody like me to bring in somebody for a Q&A and then have all the microphones stay dead. Okay. So as far as this, statistics are concerned, statistical measures, it it doesn't appear to be something you guys, especially the inferential statistics, doesn't appear to be something, but for your own professional development and whatnot, if she is going to be basically um, the last session we do of that really talks about statistics, other than running them in Python or querying up something in SQL that might be statistics. So that'll be the end of the theory this week. Okay, so I got pretty much everybody's draft Excel worksheet, and I can kind of tell where you're going. They were in various states of cleanliness and whatnot. I didn't download them all and looked at all of them in Excel. So the preview that I get in Canvas may have kind of distorted some of the columns and whatnot. But other than that, I can tell where you're going. Um, a few of you use the comments section to let me know kind of just what question you'd be asking of this data. And again, most of it's correlating stuff like that. But I was hoping to talk to a couple of you about what direction you're going and what more you think you might need. A few of them came to mind. Thomas, were you the one that had the helmet loss spreadsheet?
Yes.
Um, can you tell us where you're going with that and where you're at so far?
All right. So I think my initial thought was to try to, you know, see where the data is pointing, which I mean, it's probably pretty obvious, but see where the data is pointing on, how, whether or not a helmet should be, required
Mm,
versus, optional. Like I said, it's probably going to be overwhelmingly obvious, but that was just a topic that kind of interested me. And so there was a couple of other items I was going to add to it. I've got them written down here somewhere, but I was having trouble finding data for like the same time frame that I found the others.
hmm
and stuff. So I'm trying to get everything kind of in sync before I throw it all on there. But I had two or three other categories I was going to put in there, um, like percentage of people that died even though they were wearing a helmet versus people that wore it and or didn't wear it and died. But
Mm,
just things of that nature, just to kind of examine the thing as a whole, without assumption, I guess is what I'm saying.
sure. And yeah, a lot of things you go in when you create a hypothesis, you kind of have a an anecdotal, everybody has, kind of what they think would be intuitive,
Right.
but yeah, I thought that was interesting. Can you go ahead and mute your mic, Thomas? There we go. There's somebody's really having an active conversation right outside your cubicle. Thanks. Um, yeah, I wanted to bring that up real quick. So just share my whole screen. I got all kinds of garbage going on here this morning, playing with stuff, and didn't come to a huge amount of resolution. For Thomas's pull up Excel, I wanted to open your motorcycle fatalities. I got a copy of it in my downloads. Um, is everybody seeing this spreadsheet good, well enough? Um, One thing I did in playing with this data, Thomas, was I modified this Colorado category. Seemed to stand out. The rest of them were all this requires helmet was categorical data. And it was it looks like a fairly small number of things. So one of the things I did in the data cleansing, rather than have an outlier category with only one in it, I went in and um, got rid of that so that it looked like all the other 17 and younger categories. And then just out of curiosity, and um, I, I apologize. I've been really trying to find an Excel expert that can just roll through pivot tables. I've been clawing through the material, and it's the best way to learn, but it's a horrible way to teach. Is to to dig through material really slowly, which I'm trying to avoid in front of you guys, and just instead just let you have the time to practice with this stuff. But I did want to a pivot table, and there is a fantastic chapter, chapter 30 in our book, um, that walks through. We've got the sample data. It walks through how to do a pivot table, what a pivot table is. But just for those of you that haven't used them, maybe you've heard of it but don't really know what a pivot table does, uh, to me, is let you summarize and kind of categorize data in a smaller spreadsheet. Like for instance, rather than going through here and adding up the numbers of fatalities where you had no law, say that's the one I think Thomas was instinctively thinking you'd have a high incidence of fatalities, maybe relative to the population. And like you said, Thomas, maybe there's even better things to compare that raw fatalities number against. I mean, because you would think a large state with no helmet law would have the most fatalities, right? I mean, the highest population, most number of riders, no helmet law. That's kind of the hypothesis is that they would have a high instance. But pivot tables, and again, if Excel is in your future, chapter 30 is one of the best chapters, bang for the buck, in our book. But you just go to insert, and then I tend to start, since I'm a baby Excel user, I go with the recommended pivot tables. It's just like when you go insert recommended charts. Excel looks at your data and it guesses as to what what you're doing. So I just stuck in a recommended pivot table um, with these and chose the most one. It's the sum of fatalities by age group, and by default it sticks that in a new sheet. So you've got your original data sheet here is sheet one. Um, you can stick the pivot table in the existing sheet, um, but by default it does here. So this is um, by default, a typical pivot table activity when you've got very limited data like that. Now, the more columns you have, the more you can do summaries and subtotals and whatnot within a given category. Like you may have um, you know, products sold by region, and it'll group that, in each region, it'll show you the products that are sold and how many were sold, and then shows you the next region, the same products and whatnot. So if you're doing that sort of kind of tabular summary data, um, you the more you play with the pivot table, um, the more confident you'll be, and the more you'll be able to glean information out of it. And they make a pretty good uh, presentation. You know what I mean? If you copy pretty up a pivot table and paste it onto a PowerPoint or something for management, it it does a pretty good job of summarizing this kind of data. And that's like I said, that's chapter 3 or chapter 30 in the book. But I also wanted to show you something that you might take advantage of while you're hopefully, I really hope you guys used the final 2 hours last Thursday to do your projects and to work on class material. Um, I know it can be tempting to get sucked back into work, but I really hope you'll use the time to go through this material. And then what was I talking about? Oh, when you say file and you go to you're going to pick a new. Did everybody notice that you've got these tutorials up here? There's a pivot table tutorial. Um, there's a formula tutorial, and that formula tutorial walks you through. It's pretty slick. Let's go. It's pretty slick. It walks you through the mathematical formulas, and then there's on the on the page. It's almost like an interactive textbook. So again, some of you have barely mentioned Excel as being part of your life. So, I don't want to go and try and make you a 1,000-page expert on Excel. Um, but I did want to put these materials in front of you, these references, resources. If this is something that your employer is hoping that you'll learn and know, this would be a great way if you're not used to the concept of formulas and functions. If I want to do something, I said, since I've been a programmer for a while, I kind of know how to Google what it is I'm trying to do. But if you're not used to working with formulas and functions and deriving data from a couple of other columns kind of thing, um, uh, this tutorial is really good. So that's whenever you go to the file menu, it's one of your templates. Um, I think I can close that out. It is its own. Yeah, it opens up in its own workbook. But there's just no end of these, and it automatically goes across these tabs. Um, so that's what it covers. But there's like a next button when you're working with it. Next step. There you go. So I thought that was pretty cool. So I would recommend if you're an absolute Excel newbie, both of those tutorials, along with working with the sample data that comes with our textbook. So that was a quick plug. No, don't save any changes. for what a pivot table can do for you. And like I said, Thomas, if you pull in when you start to add this alongside something like population or number of motorcycle or registered motorcycle owners or something like that, that gives you a apples to apples proportion. Plugging that into a pivot table maybe more informative than running any necessarily kind of statistics. And again, the statistical test of the category of um, helmet law versus fatalities, I'd have to do some research. I think you would need to rank those categories and make them. There's a word for it. I covered it in my first lesson. When a category has an order to it, ordinal. Yeah, ordinal. uh, an ordinal category, you might want to make that from like a low to high as far as the restrictiveness or something like that, in order to do a no kidding statistical test between the law and the number of fatalities. And then it may be that you want to derive a field that is fatalities per capita. That in and of itself um, gives you a single column that is derived from population and fatalities. That would give you the apples to apples, so that you're not taking fatalities in a small state versus a large state out of context. So okay, wanted to make those points. There is another uh, function in Excel that I want to make sure you guys are aware of. Um, and it's the data analysis tool pack, and it's an add-in. I want to say it's 33, chapter 33. Yeah. So everybody's got Excel up, right? Um, pull up Excel. So yeah, here's my project I've been working with. And look and see. You probably, or well, you may if you've been working with Excel for a while. Like who's been Damon or Laura, a couple of you veteran analysis warriors. Do you already have the analysis tool pack loaded? Damon or Laura?
Yep, I use it.
I don't have that loaded.
Okay. Well, alrighty then. So what this thing is an add-in that doesn't cost any money, but um, you have to enable it. So if you don't have this, go ahead and follow along here. Go to File, and again, this is if you've got your Excel Bible up. It's like page 2 of chapter 33, the instructions here, but it's pretty easy. You go to File, and then down here to Options. We're starting the add-ins runtime. Just a moment. I see at the bottom of my Excel screen. I don't remember there being. I added this a year ago or better. I don't remember there being such a delay. Did what's y'all's screens good? When you said file options, did it come up quickly or?
I don't see an option tab on my when I hit file.
It's at the very bottom.
Hmm.
It was on mine anyway. Let me close out a couple of these tabs while it's thinking.
Mine came up pretty quickly, and I think I got it installed.
Yeah, it's an add-in. You just click on the you go file options, click on the add-ins tab, and you mark the analysis tool pack dash VBA and click OK, and it should come right up. Yeah, Chase, when I hit file down here at the very bottom left hand corner, you don't see an options tab.
No,
Are you
I'll find it. I'll find it.
are you on a Mac?
I don't know if
I
you can
am.
do
I am.
add-ins on Excel for Mac. You're on a Mac, right?
Yes.
I don't think you can do add-ins on Excel for Mac. I have to do a virtual.
Oh, good.
My goodness, boy, you just keep seeing evidence of that Microsoft Apple open warfare, don't you? Well, okay. I mean, I'll show you a thing or two of what it does. But yikes, if you are working with statistics, this makes running all of those statistics pretty easy. Maybe there's an add-on for Apple users. Laura, is there maybe a different third-party kind of extension?
I know a lot of there are like formulas that can replace some of what the tool pack does. So if I'm in Excel for Mac, but I have a Windows machine, like a virtual machine to run, because there's like a couple of things that you can do in Windows that you can't on Mac.
For
Okay.
Mac or Excel, it says go to the insert button at the top, and then there should be an add-ins.
Ah, thank you, Gabe. Good Googling.
And I did
Insert.
find that, but everything's grayed out. Like get my add-ins and my add-ins. It doesn't.
Okay.
That's
Well, if you don't get it figured out, give me a holler, and
Okay.
I'll add my Google into it. Although I don't have a Mac in front of me, so I'm useless to you as far as helping to troubleshoot.
yes. I will figure it out.
Yeah. So I've already got it going, so I'm going to go back to where I was. We're starting the add-ins runtime just a minute. That kind of bugs me. I'm going to close out of Excel and get back in. And there's this is the sample data from one of the files associated with the textbook. Close out of that. Okay, and bring Excel back up. I don't like it working on something in the background there. Okay, so yeah, I was working on V2 happiness. I started adding I'm looking at a raw happiness score, and I was going to contrast that against like temperatures or try and find some correlation. Now, the overall study looked at a whole bunch of factors and did a weighted assessment of people's happiness and the state. I was mortified to find Arkansas. Look at our happiness score, 36.83 compared to Hawaii at 69.58. So I had to, that's another rabbit hole I went down. I swear. I don't
Which
ever
one has the highest score?
it's high score wins. So Hawaii's um
The highest.
the highest and the happiest, and we were number 49 ahead of only West Virginia. So I guess they use several factors. Well, here it's um which one? Happiest states. This is the website for it. Wallet Hub. If you Google list of states by happiness, you'll see the same thing. But I was using this as my, kind of my data scrubbing, trying just to get this total score column, which took just a couple of cuts and pastes into a worksheet. But yeah, Hawaii is the happiness, but they group it by several categories. If you go down here to the study, here you go. share of depression, your sleep rate, participation in sports. We were pretty low. Arkansas is 46, which I don't think they're counting hunting and fishing perhaps as a sport. But they don't give you the raw data here, so you can't look at exactly what they had. Working hours, suicide rate. So they looked at a bunch of different factors and came up with this aggregate happiness score, which I don't necessarily. They made a lot of assumptions as researchers that these things correlated to happiness, but I don't know necessarily. Yeah, feeling safe. We're pretty far down on the list of feeling safe. We don't do sports. Anyway, yeah. So here's your panel of PhDs that decided the constraints, and any research project's going to publish, the rules of the road for the study. But anyway, I just wanted to. I just wanted a quick and easy column to do something with in Excel, and I wound up blowing an hour reading about this methodology of the study. Anyway, relevant metrics, but you can't read someone's mind. Happiness is subjective, but they tried to make it more quantifiable.
A lot of tourists in Hawaii.
Do what now?
A lot of tourists in Hawaii.
Yeah, there are, and aren't they happy? Yeah, I'm on vacation. Duh, yeah, you don't go to Disney World, the happiest place on earth, to ask. But they didn't ask. They used measures that have been proven to be associated with happiness in other studies, and therefore they can derive these weighted scores. So anyway. What was I going with that? Oh yeah, the analysis tool pack. So if you guys would interrupt me if you had any questions or concerns or comments or anything like that. We know that, right? Okay, so if we go, just click in a spreadsheet, pretty much anywhere in your spreadsheet, and then this analyze data. No, I'm sorry, that's not it. That's not the one. It's data. You click on data, and then data analysis. That's it. Because there's several magical tools in Excel, but this is the data analysis tool pack. So you click on the data tab along the top, and then way over on the right, where I've got it anyway, is data analysis. So you click on that. And it wants to know, what do you want to know? What do you want to analyze? So, for example, I just wanted to look at the descriptive statistics for a column. And I wanted to talk a little bit about descriptive statistics before Brian comes in and finishes with his lecture. Okay, so descriptive statistics will bring up, it's one column, right? It'll give you the mean, min, max, mode, range, all that stuff of a column. So when you click on descriptive statistics, it wants to know which column, what do you want to do it on? So I chose population. And then if you don't click labels in first row, it'll barf because it sees numbers in population. That's the technical term, by the way. Barf. It sees numbers and that header will screw it up. So always say labels in first row if you have a label. And then I always like to put it in a new worksheet, just to keep the clutter from going on. And I click on summary statistics. Now here's another interesting statistic, is your confidence level for the mean. That's based on how spread out the data is. But I'm pretty sure Brian is going to talk about confidence intervals when we do hypothesis testing here at 10. So anyway, that's what I clicked on and say okay. And then in a new sheet, you get these descriptive statistics. So the mean population is 6 million, but there's an enormous standard error. You've got, states like Texas, California, and Florida that are so humongously populated compared to Alaska, Wyoming, Montana, that the data is really not super normal. And there were a couple of scores here that I just kind of wanted to summarize. Kurtosis is how normal it is versus super narrow or super flat, right? And that score of 8 is really bad or really, not normal. I had to pull up a tutorial, sure enough, and it was summarizing. Is this the one? Interpreting kurtosis. Yeah. But it was telling me the values. Is this the one? I apologize, guys. This may not be the tab I was using. No, that didn't look right. And Zoom controls are over the top of my tabs. So that one. Nope, that was calculated. Measures of shape. Here we go. Kurtosis. So there's the visualizing it. Remember the if it's a super peaked distribution, there's much more chance that you've got to have your samples real close together, or the chances are they're going to be really close to the mean. That's what kurtosis is, as opposed to being super spread out. And there's the computational thing that we did not have to do in our own formula in Excel. And then there's an inference or interpretation. And I want to say it's down around one way or the other, makes it fairly normal, but our score up at 8 is not very normal. Skewness, we've got a positive skewness at 2 and 2.6. That's really skewed, because again, we got these gigantic states, just a few of them skewing the data. But this data analysis tool pack will do all of these things for you, instead of you having to write an individual formula to do any of this stuff, or sorting and filtering. Like to find the min and the max, all you do is go over to the data and sort, right? And you can look at it, and then, but to find the range, you'd have to write a formula. Well, this data analysis tool pack does all of that for you. But then I wanted to say you can do, oh man, where's all data? You can also do in data analysis, you can also do a correlation between variables, and it really helps to have a solid understanding of which measures correlation. So for this one, we'll say I'm going to measure the correlation between happiness and population, as to see if there's any relationship. So input range, you click on one of your columns that you want to correlate, and then I want to say you hold control on a PC and do the other one. So now it knows we want to correlate these two columns. And again, always, always remember to click in labels in first row. And then you say, okay, must be a contiguous reference. What did I do wrong? New workbook? Mm, Cancel. Flying without a net here. Trapeze without a net. Data analysis. Correlation. I could have swore this worked like a champ last time. D and E in columns. Labels in first row. In a new workbook. Does anybody see what I'm doing wrong by chance, or has been able to correlate two values? Input range must be a contiguous reference. Huh, because I would swore that I ran this earlier when I was getting ready for class, and it showed very little correlation between, yeah, in fact, there it is. I'd correlated happiness and population, and the score was 0.1, so that's very loosely positively correlated, which I wouldn't think a populated state would necessarily have anything to do with whether or not the people are happy or not. You know what I mean? And sure enough, in that study, I don't believe they looked at anything like population density, which would be more informative than just raw population. But I don't know. I'll have to see if I can get that to work on the break. I did the same thing, and it came up with this little table. This is what you get when you run a correlation between happiness and population. But there's all there are all those other statistical tests as well, for you to choose from. And like I said, that's chapter 33 in the book. Will walk you through, and it does a pretty good job of describing which of those tests to use. So that's something I'm hoping will be useful as you finish out your Excel states project and you start to look at how these columns are correlated. You can use tests like when Thomas has the categories for helmet law restrictedness. You can correlate that to per capita fatalities, and that would give you your mathematical measure of correlation between a categorical variable and fatalities. Okay, well, those were the two tools I wanted to go over. Like I said, any questions? I know I'm telling you about something as opposed to giving you like methodical tutorial on it, but it's really much better to just do the tutorial and the book and use time for hands-on. Okay, any confusion as to where I'm going with the states project? So when we're done messing with that next week, you should have some sample questions that you would want to answer. The raw data and the nice finished spreadsheet with a few columns in it, and then some statistical measures and an appropriate visualization for how those relate. And then I just want to everybody to kind of present that, like just as a quick 5-minute TED talk of I wanted to know how these variables related. This is where I found my data, and this is what I found out. This is what my findings were. And that can be in raw data. It doesn't necessarily have to be in these chi-squared tests and t-tests and ANOVA and all of that. It can just be the reporting of the data as you found it. Okay. No questions, no concerns. All right, you're letting me off the hook. So let's take a 45 minutes for our normal break, but then 30 minutes to get back on your please use the time to work in your spreadsheet, get things cleaned up, and if you haven't turned it in, try and get it in sometime today. If you make progress on it, or when you make progress on it, use the comments in that assignment. It's overdue now, but don't worry about that or the score or anything like that. But use the comments, or put your research question somewhere obvious in your spreadsheet, so I can kind of I don't have to assume. Some of you had quite a few data items, and I couldn't quite tell what sort of um, analysis question you were heading towards. So please be back at 10 for Dr. Brian Aguiar and a wrap up of this whole experimental design inferential statistics topic. Okay, I'll put up a whiteboard saying as much. See you guys back here at 10. Welcome back, everybody. And I've asked a colleague of mine, Dr. Brian Aguiar, to come in and put a kind of final stamp on this whole notion of a hypothesis and hypothesis testing, and somewhat of the inferential statistics and confidence intervals and those sorts of things. And again, Brian, for your for your background, these folks are all working analysts. None of them in a clinical scenario where you would do your classic kind of hypothesis testing and whatnot. So this exercise is a little bit academic, but I think I would be remiss to not have this in their toolkit going forward.
Mhm.
So I'll let you take over, man.
All right, appreciate it. Is there any way you can let me share my screen?
I think participants, and then make you a presenter or something like that. Is that?
I think so.
More. Make host. I remember how to do this for in Collaborate Ultra. I'll just make you the host.
Okay. Collaborate Ultra. There's something I hadn't heard in a while.
Yeah, we went away from it. I was using it for the last time I did one of these cohorts, and it just was too framey. It just seemed to have performance issues.
Yeah.
And I stopped using it and went back to Zoom.
Yeah, the time I had to use it, I had nothing but trouble.
Yep.
So I'm also back using Zoom. Okay, well, I just wanted to kind of share some slides and just kind of go over some of the concepts, just kind of review some of them. So we have a common frame of reference here, and then we'll get into looking at some data and looking at a different tool. I don't always use Excel. I don't think there's anything wrong with using it, but there are some other tools that are out there as well that you can use. So this was kind of the topic that I was going to talk about: experimental design, inferential statistics. As you know, descriptive statistics, we're trying to just describe data. Maybe we're talking about what our current data shows, but we're really not necessarily trying to go beyond the data that we're looking at. So with our inferential statistics, then we are trying to reach conclusions that extend beyond our immediate data set alone. Several years back, where I work as a full-time faculty member, we had a vice president of education or learning that quite frankly, I didn't care for, but just for full disclosure. So he really didn't win over me with anything he was doing anyway, but he would always talk about the data, and he would make lots and lots of changes. And every time he made the change, he'd refer to his sample data that after he made the change. And I would always say, well, how do we know? We haven't compared it to anything. We haven't done any hypotheses testing. So how do we know that your change is actually what made this difference that you're claiming? And in several cases, when I did do some of the analysis, I showed him that, oh, by the way, we probably would have had that same result had you not made that change. So from our perspective, it wasn't that big of a deal because it didn't cost a lot. But certainly if we're putting a lot of resources, either time or money into something, then we might want to know that it's actually making a difference. Okay. Again, just as a refresher, population versus sample. The population is what we're really interested in. We have a sample to work with. We get our sample results or our sample statistic, and then we're using that as our estimate of our population. We have our point estimate, which is that single value. And then, as Don said, we have interval estimates or ranges. I just think of an interval estimate as a range of plausible values. I don't know the exact value of that unknown population, but I can build a range of plausible values that I believe it is. And again, typically we use a confidence interval and we establish some type of confidence. Now, the thing about the confidence interval that we have to keep in mind, we're not saying we're 95%, say, if that's what we use, confident that this interval contains the true population parameter. What we're saying is if we did this sampling over and over and say did this 100 times, we would build 95 intervals that would contain the true population parameter that we're interested in. Okay, it's a slight twist on the definition. Sometimes we forget that because our interval that we build at any given time, if I'm trying to estimate what the ages, say, of my students, when I say that I have a range of 18 to 21, that either contains the true population average or it doesn't. I'm not 95% confident. I'm just saying if I did this over and over, resampled, then I could build. All right. So this slide, I like this one because it just kind of shows us that, here we have Massachusetts, or as when I lived back that way, I would call it Taxachusetts because of the state income taxes and such. So we have this blood pressure that's 78. And we know that when we take samples, we're not going to get exactly 78. Okay. So we might take a sample and get a sample mean of 67, or we might take a sample and get a sample mean of 75, or we might take a sample and get a 71.3, as these three samples show. These are all possibilities, even though that mean in the population is actually 78. And so this is the idea that we want to express with our confidence intervals is now I don't have anything here with our standard deviation, so we can't really build or do this, but we know samples are going to vary from sample to sample. These are three legitimate samples that we took from this population that had a mean of 78. Okay. So we don't really know, when we're doing hypotheses testing, we don't really know what that number is. Is it 78 or isn't it? We can build confidence intervals based on our samples, and we can get a feel for what that true number is. Okay. We're going to look at some examples. I just wanted to go again just over some of the terminology again, just so we have a common frame of reference. All right, so hypotheses testing, then it just gives us a way to test assumptions. So in that previous example, I may have had an assumption that it was 78 or it was some other number. And I'm just going to take a sample, and let's see if I can go back. Usually can't when I do this, but we'll try. I think I went back. So I might take a sample, and let's say that I start with the assumption that it's 78. And then I take the sample, and my sample, I get an average of 67. Now my question becomes, my hypothesis test, is my assumption still accurate based on these sample results? Or is 67 far enough away from 78 or whatever number I had, 75, to suggest that my hypothesized value is wrong? Okay. Lots and lots of different ways we can do that. I believe in a previous discussion, you've talked about ANOVAs, you've talked about t-test and things like that. So there's lots of different ways we can do hypotheses tests. These are just some of the general steps that we follow regardless of what we're doing. You know, the first step is always identify or define our problem. In this case, we do it with a null and an alternative hypothesis. We want to examine the data and check the assumption. Oops, sorry about that. Just trying to open my soda. In that, we are typically, whatever statistical tool we're going to use, there's certain assumptions that go with those tools, such as, is the distribution normal? Does the data follow the normal distribution? What's your sample size? Do you have a big enough sample size? Those types of assumptions. And so we want to check those because we don't want to use the wrong tool for the wrong reasons. If you read a lot of published research, one of the things I always do recommend that anybody do is look at the assumptions that were made, look at the tool they were used, and see, did the data fit the tool? Because oftentimes you'll find, unfortunately, everybody has to take stats class when they're in college, and we don't really get a full understanding, and we learned a particular tool, so we just always use that tool as opposed to maybe the data didn't meet that assumption. I like to use a screwdriver for everything. I use a screwdriver as a crowbar. I use a screwdriver as a chisel. And every now and then I even use a screwdriver to drive screws in and out. But you know, that's what it's really designed for. You're not really supposed to use it as a chisel or as a pry bar, but I do anyway. So that's our step 2. We want to kind of make sure we're applying the appropriate tools. And really that's through the assumptions the tool has. Then calculate test statistic and our p-value. Typically, if depending on when you took stats, you may have had to calculate z-values manually using formulas, or if you had ANOVAs or things, you may have used formulas. That's our test stat. Fortunately, today with automation, with computation such as TI-83 calculators, Excel, other programs, all that brunt work can be done for us. Typically, if you're taking a class where you had to do those, that's kind of what you focused on because you wanted to get your calculations correct. You know, because you had a test or a homework assignment to get points. So you really might not have had a lot of time to focus on the idea of what exactly are you doing here, and then what exactly are the results telling you, because you were really worried about, can I use this formula correctly and plug in all the numbers and come up with the correct answers? And sometimes you had to decide, which formula do I even use, and then plug in all the numbers and see if you can come up with an answer. Okay, but now that's a lot easier. And then we have to make our decision. All right, we have to decide, and our decision is always about the null hypothesis. So the most common example that's used in explaining hypotheses testing is typically a criminal court trial in the United States. With a criminal court trial, we start off with an assumption, okay, and that is our null hypothesis that we assume, sorry, I didn't mean to advance the slide. We start off with our null hypothesis that the defendant is not guilty. The alternative is they're guilty. Guilty is what the prosecutor, of course, is trying to show. All right. We're not trying to prove the person is not guilty. That's our default assumption. That's a common thing we have with a null hypotheses testing. When we get through the process, we often think we're trying to prove the null hypothesis. We're really not. We already assume it's true. What we want to do is find evidence to suggest the alternate hypothesis is true. So just as with a criminal trial, the prosecutor is there to present evidence. So that's our steps 2 and 3, right? They're going to examine the data. They're going to present the data. The defense attorney is going to question the data. And then, it's up to the jury to calculate, if you will, their test statistic and their p-value. In the case of a criminal trial, beyond reasonable doubt. All right, that's too vague, obviously, for statistics. So we're going to use some type of a p-value. Typically, we use a level of significance of 0.05 or 5%. And then we're going to make our decision about that null hypothesis. Do we retain the idea that someone was guilty or that they were not guilty, or do we reject that in favor of the alternate? And the alternate, the only thing we have is guilty. Okay, so that's kind of the same idea of hypotheses testing. We're looking for the data to kind of support. So here's an typical example of one sample hypotheses test. We have some type of a target value. Manager wonders, are we actually delivering on average in less than 20 minutes? Of course, we're going to have some deliveries that are going to be quite a bit less than 20. We may have some that are over. We might have some real close to 20. So we want to know, overall, are we meeting that average? Because even if we are, we may have, on certain occasions, deliveries that go beyond 20 minutes. Some of those might have extenuating circumstances as to why they do. There's a car accident, there's a traffic jam, something like that. My background before teaching was in the Air Force and logistics. And so I used to do a lot of planning of things. So I had something planned today. I have to have my toilet replaced in my master bath. So I had it all set up for the toilet to be delivered between 8 and 8:30, the installer to be here between 9:30 and 10, and just have the job going. Well, come about 9:25, I got a call from the installer saying he had a family emergency and he wouldn't be here today. So, that's one of those assignable causes that kind of happens. That's going to happen now and then. But overall, as we are saying with this example, are they being delivered in less than 20 minutes? Okay. Also, we can do 2 samples. Here we might want to compare from the difference here. We're looking at mean mass body weight, body mass index rather, for males and females, and we want to know, is there a difference? So now, rather than comparing one sample to some target value, less than 20 minutes, now we're going to compare differences between 2 groups. And in previous material, you looked at a t-test. That's what we can do with a t-test. We can compare 2 groups. We could also compare more than 2 groups using the ANOVA if we wanted to go that route, if we had other groups that we want to do. Okay, but that's just kind of the difference. But that first step is always that, I always say, that critical step, because we really don't want to end up solving the wrong problem or looking to the wrong problem. So we want to identify what is it that we're trying to do, and then we want to write that hypothesis as such. So here we were looking for the difference. So, okay, between the 2. Okay. Oops, I went backwards, I think. Let's go the right way. Okay, so again, checking the assumptions. This is a big step. These are just some examples of some assumptions we might have. One of the big one is that we use some type of a probability sampling method in order to collect our data. And we could spend hours and hours talking about probability sampling, of course. Typically, we mean some type of a random sample, whether it's a simple random sample or whether it is a stratified or something other than that, a cluster random sample. But how did we collect that data? That's very important, because most of the tools assume the data was collected using a probability sample. I'm just going to take a sip here, just one moment.
While you're sipping, Brian, I just wanted to jump in and get you to clarify that H0 and H1 notation.
Oh yeah, okay. Yeah, please stop me along the way if there's something I need to clarify. Okay, so what we're saying back here, when we talk about the null and the alternate, H sub 0 is the null hypothesis. That's the one we assume is true when we start our testing. That's the one we're trying to find the evidence against. Okay. H1, and also it's oftentimes labeled, since it is the alternative hypothesis, as H sub A. Okay. Typically, HA is what you're trying to prove. You're trying to support with your data. So as I said, in the case of a criminal trial, H sub 0 would be not guilty. That's what we assume. HA or H sub 1 would be the alternate, the defendant is guilty. So the prosecutor is there. We want the evidence. In our case, it's going to be the data to support rejecting the null. And then we found support. So again, oftentimes we get this backwards because we think we're trying to prove or support the null hypothesis. Generally, when we're trying to do hypotheses testing, we're going to assume whatever we believe is wrong. So in this case, where we have H0, the mean is greater than or equal to 20, the manager is assuming that the claim is wrong. They're not being delivered in less than 20 minutes. Until the data shows otherwise, she's assuming that she's wrong. And that's a little bit different. You know, Google is a wonderful tool, but you know, you can call Google the great confirmation bias, because you know, if I believe the world is round, I can find enough data on Google to support that. If I think it's flat, I can probably find enough evidence to support that. And probably if I feel it's a triangle, I could probably find enough for that. So yeah, we're assuming we're wrong in this case, and then that it's greater than 20 until the data shows. Two samples, same thing. We have an H sub 0, the null hypothesis. We start out with the assumption that that is correct. So in other words, here we were looking for a difference. We're saying there is no difference. They're the same until the data shows us that they are different. And that's where our H1 is. We're saying that they are different. So every time, there's a lot of ways we can set these up. I always like to say, aim for what you're trying to show in your alternate hypothesis, whatever you're trying to support with your data. So in this case, I'm trying to show that I'm asking the question, is there a difference? I'm assuming there isn't until the data shows me that there is. In this one sample, my claim was that, you know, are the times less than 20? I'm assuming they're not until the data supports that they are. Okay. All right. So again, the assumptions, lots and lots of different assumptions. It really depends on the tool. Probably that last one is probably the most common assumption that we have. Here it just says both because I was going to try to focus on two sample, but typically if we're going to use t-tests or z-tests or ANOVAs, we have this assumption that the populations are approximately normally distributed, or that sample sizes are large enough. And typically when we're dealing with means, we're looking for our sample size to be greater than 30. If we're dealing with proportions, then we have a little bit different. Other assumptions, when we're doing the t-test, when we have two populations or two samples that we're comparing, then we want to know, are they independent or are they paired? Then we have a subcategory of independent. Do we have equal variance or do we have unequal variance? All right, so, you know, lots of different assumptions. And whenever we use a tool, we just kind of want to check those. If they're not met, then we want to at least be able to address, why is this tool still appropriate if we haven't met those particular assumptions. Okay. All right, then the calculate the test statistic and the p-value. Test statistic is nothing more than whatever distribution you're using. You've probably used a Z distribution in your life. You've probably used a T distribution, particularly if you had to take any type of stats classes. You may or may not have used a F distribution or a chi-square distribution. Right? But all you're doing is you're just converting your results that you get in the first example that I used was the time. So I would have recorded the amount of time it took to make deliveries of sandwiches. And then assuming I'm using a t-test, I would have converted those numbers to a t-stat, just how many standard deviations are my result away from what I was hypothesizing. And we'll look at some examples when I get to a little bit of a demonstration. The old days, you had to have tables. You had to have T tables or Z tables or F tables or chi-square tables. Back when I went to college, I carried around a Z distribution folded up in my wallet because we were always using those. So I always wanted to make sure I had one handy. And so, now it's great. Just about all your software, you can just punch in the information and you can get that taken care of for you, calculate the test statistic for you. And then rather than having to use the tables, you can just do the p-value approach to make your decision, which we'll talk about in a moment. Okay, so here's that moment has come. So again, we assume the null hypothesis is true. Again, I like to think of it as generally, I'm wrong, whatever I think I'm wrong, okay? And then I want the evidence or the data to show me that, hey, maybe I'm correct. Rule of thumb, if the p-value is low, then we reject the null hypothesis. Now you've found evidence to suggest whatever it is you were testing is correct. Okay. What does low mean? Relative term. Typically, we have some type of level of significance that we're comparing to. And again, typically it's going to be 5%. But we could use any level of significance we wanted. But the most common one is 5%. And there's a lot of rumors about why that is so. And it really just goes back to the old days of before you had calculators and ways to compute things. If you remember from your stats courses at some time, the standard distribution, one standard deviation plus and minus was 68% of the data. Two standard deviations was 95%. So what's left over? 5%. So 2 was a very easy number to work with. I could throw out any number and ask you to divide it by 2. You'd have the answer in no time. I could have any number and I could throw it out and say multiply by 2. You'd have the answer in no time. But if I threw out a number and said, okay, now multiply or divide, let's say divide that number by 1.347, now you've got to stop and think about it. So that's the only reason 5% became the standard, is just because that represented 2 standard deviations away from the mean. Gave us that 95% confidence, 5% significance, okay? So again, in other words, if a low p-value indicates an odd result, if in fact the null hypothesis were true. So let me go back to my criminal trial example. So let's say that I'm being accused of robbing a liquor store. Something I was suspected of at one time, only because my car I was driving past, I worked in a restaurant at night and somebody robbed a liquor store and took off in a direction that I happened to be going home at and got stopped and all this kind of stuff. And because it was an armed robbery, they came out with guns and everything. It was quite an interesting situation. But let's say that that happens, okay? So, all right, we assume we're not guilty. Now the prosecutor presents evidence, the first piece of evidence. Well, there's a video and it sure looks like you walking in the store, robbing the place. Second piece of evidence, you work at a place that you wear a name tag and it says, "Hi, my name is Brian." And boy, that person in the walking in that video has a name tag that says, "Hi, my name is Brian." Okay, so now we get another piece of evidence. Then they say, they put my mom on the stand, and my mom said, they asked my mom, "Hey, do you think Brian robbed that liquor store?" And she says, "Oh yeah, that's all he's talked about for days. On Friday, he was going to rob the liquor store." Okay, now there's another piece of evidence. Now keep in mind, the assumption is I'm not guilty, but everybody on that jury is going, "Wait a minute, that's his mom sitting there, and his mom said he's going to rob it for days." And now finally, the piece of evidence that convicts me is there happened to be a busload of nuns broken down in the parking lot. The bus was broken and they were waiting. And since I was raised Catholic, when I came out of the liquor store with robbing it, I jumped on the bus and said hi to all the nuns and said, "Bless you, sisters." And they said it. And so there's 30 nuns on that bus, and every one of them sat in the witness chair and said, "Yeah, that's the guy who jumped on the bus," and shook my hand and said, "Bless you, sister," or whatever. Well, at that point, if you've ever been in a criminal trial, you know it's almost impossible to beat a busload of 30 nuns. Okay, so pretty much now, when the jury deliberates, it's not going to take them long. They're going to sit there and they're going to say, what's the probability that this guy didn't commit the crime? The video guy looks just like him, wearing a name tag that says, "Hello, my name is Brian." He wears a name tag to his job that says, "Hello, my name is Brian." His mom said he talked about doing it before he did it. And then 30 nuns sat there and said, "Yeah, this is the guy that jumped on the bus and talked to us." So in other words, this would be very odd results to get if in fact the null hypothesis were true. And that's really what we're doing in our decision. That's why I just say p-values low, lower than whatever standard you've set, reject the null, because it means it's a very odd result if in fact the null hypothesis were true. Okay, so I wanted to demonstrate using this particular software, Statistics Open for All. I don't have any claim in it. It's free. You can download it for Windows, Macs, Linux, whatever you want, really. But I think it's a friendly, easy to use software. It's a little bit more, I think it's a little bit more intuitive than using some of the features of Excel and some of the data analysis tool pack. One of the colleges where I teach, I'm required to use the Excel data analysis tool pack, but it's not really necessarily, one of the best tools. So, whoops, there's my email. So I'm just going to open up this tool. I'm going to switch my screen share. So just give me 1 or 2 quick minutes and I'll get this up here. And I think you can see the SOFA software now. Take a quick drink. All right. So the first thing I'm going to do is just open up. This has a demo table with some data that came with it. So I'm not putting in my own data here. I just want to open this up. Because this is demo data, it only opens in a read-only mode, so I can't really change it. And that's also why all the fields are blue, is because none of them are editable. I can't change anything in this file. Previously, when I was playing with it, I added a filter, so I just want to remove that. Okay, so we have different types of data. We have some name data, phone numbers. We also have country data, and we've entered it as numbers. And each number represents one of 3 countries, either Japan, Germany, or Italy. We have different types of cars, all represented with a number. We have gender, male and female, represented with a number. And then we have some actual numerical data. We have age, which is a number. We have weight, which is a number. And then we have weight post-diet. And then we categorized age into various age groups, as we'll see in a moment. And then we have web browser. Okay. I don't recall what all this data actually represented from SOFA. Okay, so again, we can look at some of the report tools, some of the descriptive statistics. Hang on one second. Just make that a little bit smaller. There we go. All right, so we can look at some of the descriptive statistics. So let's say we wanted to just kind of look at age. You know, we can see this is just our frequencies, the different age values, and how many within each grouping. If we wanted, yes, I know, I was going to say we could look at gender, for example, and then we could add to that. There we go. So here we have gender as a categorical variable that we're using. Remember, in our file, we had it as a number, but those numbers just represented the category being male and female. And so we can see that the average age, males and females, is pretty close, but we could do a t-test to see. Doesn't look like a big difference, but is that difference statistically significant, or is this just sample chance variation? So it gives us a chance here in this particular area of the program to just kind of get, we can also print the reports, but it gives us a way we can kind of look through the data, mainly descriptive statistics. We're just describing the data. We might want to look at age group, so we can see that, you know, the different age groups that we have. And then if we wanted to, we could add some type of a row status to that. Like maybe we want to know, does weight differ based on age group? Maybe that's one of our research questions. So we can see that there's quite a bit of difference here in the average weights. And then again, we might want to analyze that with a ANOVA. Since we have more than one category, we have several different age groups, 2, 4, 5 age groups. That would be beyond a t-test. So maybe we could use an ANOVA to analyze that and see, is there significant differences between these? Or one of the ones I like to use would be country. We only had 3 countries, so we might want to know. Now I left the age on there, but I could have just deleted that as well. So again, are these significantly different? The fact that people in Italy weigh whatever scale this is, 68.8, and then Germany is 71.2. Are those statistically significant differences, or is that just chance variation that we would have, that we would expect, if in fact there was no difference between them? The other nice part is we've got a lot of charts, and we have a lot more flexibility on the charts, I think, than Excel provides, particularly for categorical data. I think it makes it a lot easier to do a categorical, like we had age group was a category. I always like my pie charts with percentages. Oops. So I didn't change. There we go. I still have weight. I didn't want that in there. I wanted gender. Didn't change that. There we go. All right. So now we have all that information broken down with the percentages, each of the different age groups, and then we have it further split by gender. Of course, we don't have to split it. Could have just seen it all as one, so we could see the different percentages as well. We can easily switch to a bar chart or a different type of chart just by switching over there. If we have numerical variables, we have some of our options. So this one, let's go with age by, whoops, sorry, age by gender. Okay, so again, I can see that the side-by-side box and whisker plots look very similar. Doesn't appear to be any real statistical difference there, but we might run it through a t-test anyway just to see. Could also do age by maybe country. So there's that difference that we saw, that Italy seemed to be a little bit younger than some of the other places. Are these statistically significant differences or not? We also have our scatter plot. If we were looking at two numerical variables, such as is weight related to age? Oops. Yeah, yes, I know, I have to change this. Let me switch over here. There we go. There we go. That should work better. And I always like to show the regression line. But we'll give that a second. So there's our regression line. It gives us our regression equation, our slope, our intercept. There's some hypotheses testing we could do there. But we do see there seems to be a positive relationship between age and weight. And we do have options to filter, which if we wanted to, say I wanted to filter by country, and I don't want to include, the country numbers were 1, 2, and 3. So let's say I just didn't want to include one. So just showing different ways we can slice and dice and look at the data. Okay, so that's all our descriptive statistics type things. The stats part of it gives us some options. If we know exactly what test we want to do, we can just select it. We don't have to, I know I want to do a t-test paired, or a Mann-Whitney test, or one of these others. I can just do that. Or if I need a little help deciding, I can go here, and depending on my choices I make, it'll point me in a direction to the proper test. So here I want to do 3 or more, because I know the countries, I had 3 groups. Age group, I know I had 5 groups. So this tells me if I want to do, is there a difference? 3 or more, I need to use my ANOVA. And then of course the wonderful SOFA. If I click on that to configure the test, now it gives me an opportunity to configure the test. One of the nice parts is, since I'm looking for averages, I have to have a numerical variable. So the drop-down only gives me numerical variables. It's not going to let me take an average of gender, because gender not being a numerical variable, even though I put them in as 1 and 0 or 1 and 2, it's a categorical variable. So now I can have a weight, and I can group it by, let's do country. Okay. Now I can say, do I want to include, what's the first country and what's the last country? Now I did have that filter on, so I do want to remove that. There we go. All right, so I could only, if I just wanted to limit it, I could do it there as well. Now I have the statistical results of the F-test. Okay. We can see my p-value right here where it says p is less than 0.001. So the results I have would be unusual if in fact there was no difference in the weights between the 3 countries. Okay. So there was a statistically significant difference. Then down here, I have some of the summary data. Notice it gives me the confidence intervals, the standard 95%. 95% makes the world go round. So we have our group. We have what the average was of the people that are in our data, but in the population, that could be as low as 73, it could be as high as 77. Okay. We can see in Italy, it's between 66 to 71, we believe, as our range of plausible values for the entire population of Italy. I'm just guessing there's more than 507 people in Italy. Our sample only had 507. And then finally in Germany, we had between 69 and 73 here. So that gives us our 95% confidence interval without having to calculate it. Gives us some of those measures. I believe you talked about skewness and kurtosis, gives us those measures there. I always recommend whenever you're using any type of software with skewness and kurtosis, if there's any notes that you read them, because there are different ways to calculate it. And so you want to see how that software calculated it. So in this case, for our kurtosis, it says between -2 and 2 means kurtosis is unlikely to be a problem. Between -1 and 1, kurtosis is quite unlikely to be a problem.
So I ran a descriptive stat of populations of the United States this morning, and their kurtosis was 8. And that is showing that it's broadly variable. Brian, is that the kurtosis was 8, which I'm thinking is because there's such a huge variation between, like, Florida, California, Texas, and say Wyoming, and is that so? So kurtosis is one of the measures of not
Yes.
being normal, right?
It's about the peak, how peaked this distribution is. Yeah, you have we have extremes. So if you use Excel, I don't recall which formula Excel uses. I think Excel uses the excess kurtosis formula. So you'd want it to a perfectly normal, I believe, would be 0 in Excel. I'd have to look that up though, to be sure. Okay. So here we can see skewed. The data is really not all that skewed. Again, with Excel, the higher the number, the more skewed to the data. This one gets calculated a little bit differently. Okay. And then finally, we have this last column, which is something most of this other information you could get fairly easily in Excel. I think everything but the 95% confidence interval, the data analysis tool pack, the descriptive statistics part gives you all that information. It gives you the average, the sample size, the standard deviation. This P for abnormal here, though, that has a subnote number 7. No, you can't read it, but this is a single measure of normality. If the P is small, less than 0.01, you can assume the distribution is not strictly normal. Okay, and so we can see that everything except Germany, we have some relatively low p-values. Italy has a small p-value, so our distribution of ages in Italy is probably not normally distributed. Same thing for Japan. We have this e to the -3, so we got to move the decimal place. Only it looks like Germany is the only one that has about a normal distribution. Okay. So that might influence whether or not we're going to trust these or place a lot of faith in the results that we've gotten from this F-test, because the F-test does assume a normal population or normal distribution. However, it is very robust to outliers. So again, that would be just something we'd want to identify, say, oh, and do we want to trust these results or not? Because we can see that 2 out of the 3 don't appear to follow a normal distribution. That's one thing that the Excel output doesn't give us. It doesn't have a built-in test for the normal distribution for individual variables. There's a couple of different ones that people use, and this just gives us one common one. So that's the ANOVA. I had 3 or more. The other one I'd like to do on this particular data is with the age group. So again, I just select, I want to include all age groups. So I start with the lowest, go up to the highest. These take a little bit time to run. As we can see, the p-value is less than 0.001. So it is significant. There are significant differences in the average weights between the different groups. And you probably can't read it, but once I've selected all the different options right here, it kind of gives me the null and the alternate, gives me the hypothesis. Does average weight vary for age group between groups less than 20 and 65 and plus? So my null hypothesis, no, it doesn't vary. My alternate would be yes, it does vary. So I kind of have so I'm rejecting the null because I have such a low p-value. I would normally use 0.05. This is, p is low, it's lower than h0, or lower than 0.05. So I did find a difference. Now this gives me the individual groups, their numbers, and then it gives me the confidence intervals. So I can see that, for example, less than 20, there's really no overlap with any of these other groups. You know, my interval here was 46 to 51. My next interval starts at 65. So we can see there is some interval between these two, some overlap. This group could be as low as 65. It could be as high as 70. And this one starts at, no, I'm sorry, there isn't. This one starts at 72. All right, so we can kind of get a feel for which groups are different. This group less than 20 is certainly different than all these other groups. This next group is a bit different, but here we can see there is overlap between these two groups, 30 to 39 and 40 to 64. And we can see they're kind of close in age, 75 and 76. So there's probably not a statistically significant difference between those groups. But we can see that the other groups are different. So the F-test, however many groups you're testing, it just lets you know overall, are there some differences in between the groups? Then we want to go in and then we'd have to look specifically at the differences. Okay, so I'm going to do that because I did want to go on to the t-test. And so we're going to look at these two groups as an example. So let me close this one. So I know I want the t-test, and I want the t-test for independent groups. All right, because it's different people in those groups. I haven't paired them or put them together in any way, shape, or form. The people that are in the age group above 65 are different people that are in the age group of 30 to 35, so independent groups. All right, so again, the average I want is weight. I want to look at age group, and I want to compare. Remember, I can only compare two groups. So let me compare the first two groups. So now I have the t-test. Once again, you probably can't read it all that great, but below the results, here's the results. I have the p-value, and I have the test statistic. So I can see I have a very low p-value. So there does appear, and you know, we can look at them here, 48 to 67, probably not a big surprise that there was a statistically significant difference between those. Let's change the age groups. I think 30 to 39 and 40 to 64. Okay, now we can see the p-value is 0.3482. So there is no statistically significant difference between these two groups. Okay, which is what we had seen previously, just by looking at that output that we had over. So this would be a way for us to compare the two groups. I do want to do one of the paired tests because we do have a before and after. Your paired tests are typically, your classic example is a before and after type group. So here we have post diet or after diet weight, and then we have a column called weight. So each one of these, we have two measures from the same person. We weighed people before a diet, and then apparently they went on some type of a diet, and it could have been a weight gain diet, a weight loss diet, we don't know. But either way, we have two measures from the same person or dependent samples. Okay, and we can see there is a statistically significant difference in this. 0.001. So again, looking at the means between them, weight was 71.627. Post-diet weight was 73.6. Even though that's only a couple of whatever units these are, that is a statistically significant difference. And that's what we're trying to do with our hypotheses test. We're trying to say, look beyond just this data so we can make an inference to the population. I was part of a study, if you've ever heard of a drug, when I was in the clinical studies for a drug called Repatha for people with heart issues. And one of the things it's supposed to do is lower your LDL cholesterol. I think, yeah, that's your bad one. And so as a volunteer for the study, it was double blind. I didn't know if I was getting the drug or the placebo, and my study doctor didn't know. I was just assigned a number, and then I would every 2 weeks get the shot. Well, in between those times, I went to see my cardiologist. I had my normal appointments, and my LDLs had dropped so low, he just assumed the test was wrong and scheduled me for another, cholesterol blood test and all that. And the results were extremely low compared to before I started these clinical trials. So he didn't know I was on these clinical trials for something. And so I ended up, he did 3 tests because they were so low. And then I said, well, he still didn't, when I told him after the first one I was on this study, he goes, yeah, but that's an experimental drug. It probably doesn't work that good compared to what I was. And by the 3rd time, he accepted the fact that, well, perhaps you actually are getting the actual medicine and it does work. And so, I've been on this study for many years before it was on the market, and I'm on a follow-up study. And now it's interesting to see my cardiologist, now that's on the market, actually prescribes that drug. And he tells people he had a patient that he did not believe that it made that much of a difference. He thought the tests were wrong. So, here, it doesn't look like a big difference, 71, 73, we might say it's not, but it is a statistically significant difference. Okay. All right, I want to leave Sophie.
Brian,
Yeah.
I just wanted to, and you are welcome to tell me out of the scope of this discussion. But we saw there based on pretty much based on like the distribution of those means that the probability was very low that by chance the weight was different by 2 pounds. It was
right.
Everybody people gained on average
right.
2 pounds during that test. So let's say it's a weightlifter's diet. So what I'm trying to, and again, I am not a statistician. I'm much more of like a database developer, programmer guy than any kind of scientist. Will they design an experiment where it's worded like the null hypothesis will be like, the drug does not lower LDL by 10 points.
Right.
You know what I mean? Or do you just, you know what I mean? Like, so you have the statistical significance, but then you have the clinical significance for the before and after of what you're looking at. Can you
Yeah,
address
absolutely.
that?
Yeah, this was a new drug. It was one of the first ones on the market. And so at that point, they're just saying, okay, compared to everything that's out there, I was already taking medicine that was there and you still take it. It's for those that like a statin doesn't really do anything for you. It doesn't really help you meet your goals. So this was to see that it would actually work. But then another company came up with a similar drug. So, they might be looking for, as you said, it not only lowers it, but it lowers it more than 10 points or a specific number. So even though it lowers it, even though we found that statistically significant result of 71 to 73, even though it was only two, whatever units they are, say kilograms or something, pounds, I don't know, that might have no practical significance, or it may have no clinical use whatsoever. And that's where the domain experts, and that's where that expertise has to come in, and we have to say, okay, does this really matter? Yes, it is a statistically significant difference. This result cannot be attributed to chance. That's all a statistically significance means, is we've eliminated it's just chance results. Now, does it have any practical use or practical importance? And that's where we need our domain experts to step up and say yes or no, not really.
There you go. And that's what I wanted to drive home for this group, is that we've got folks that are in digital media, and maybe you want to measure the average time that eyeballs are lingering on a web page or an ad or something like that. You may find statistically significant, but in your before and after, say you change the design, or you change the font size or the background or whatever, and then you get some amount, some measure before and after. You guys, as the domain experts, are going to have to decide if an extra 5 seconds lingering on an ad is significant, and how you go about doing that. And we've got some folks in healthcare. So again, I wanted to drive home the difference between statistical significance in your sampling versus the practical significance of a before and after, based on whatever your domain is.
Absolutely. And I did something I shouldn't, and I never recommend doing, is I analyze data and I talked about it. I don't even know what that data represents. So I'd want to have some type of a data dictionary. I want some type of expertise before I start messing with, before I go into it. This was just for demonstration purposes, more about the tools, less about exactly what the data meant. But yes, as I said with this, when I had this VP that made changes, yeah, we saw a difference. Everybody agreed there was a difference from before and after, but my point was it wasn't a statistically significant difference. So even though it was different, you can't say that we wouldn't have had that same result had we not. Now, we didn't spend a lot of money to make these changes, so nobody really cared. But had we spent a lot of money, it would have been better to do some type of a pilot study, some type of a test. Then we could have looked and said, you know what, these changes really don't make a difference. Maybe we don't want to spend, but someone's still going to have to make that decision. All right, we found a statistically significant difference. And then someone's going to say, all right, do we spend the money to do this? And they might say, no, it's really not that big of a deal or something. I do have one last slide. This is my what I call my shameless plug for my free resource. This is my site I use with my students. It's Dr. B's No Bull Guide to Data Analysis. There's a lot of stuff in there. It's a lot of my notes, and it is a rough work in progress, process. So please, don't take it as statistical, Bible or chiseled in stone or anything like that. It's just, I find with students, if I can keep it as simple as possible, they appreciate it. And I try to cut through all the stuff. And certainly if you want a more detailed explanation of things, this is not the guide you would use. This is very, very just, brief. But the reason I like to share it is because my cover picture is me with my kitty. That's my Mad Max, and I love my boy Mad Max.
No, we don't eat our kitty.
But this is just a little guide. It's just got some of the things, just some, overview stuff. For those of you that do use Excel, because I have to use Excel with my students, there are some, like if you're trying to do the paired or the dependent sample t-test, there are examples on how to do it in Excel and how to do it in the TI-84. Because I made this mainly for my undergraduate students, kind of as a guide to help them out.
Yeah, we'll be going into Python for
Okay.
visualizing and
Yeah.
and pulling down these sorts of stats too.
Mhm.
Not in any huge level of detail, but yeah,
Python's a
Python.
great tool. Python's great to use if you use it. Yeah.
It seems like a lot of the folks coming out of math departments
Mhm.
are aficionados. But I'm kind of more of a web MIS guy, and
Mhm.
you're seeing Python much more broadly
Mhm.
adopted as it's just a general
Yeah.
purpose scripting language. So I'm going
Mhm.
with that.
Yeah.
All right. Any questions? This is, like I said, this is our last. Everybody's like, finally, our last real lesson on inferential statistics and the notion of probability and confidence intervals and how likely it is that your before and after test was just a random act of chance versus, oh no, there's something significant going on here. Like I said, we'll address it more in the future. Any questions for my friend Dr. B?
Yeah, do we use any kind of statistics whenever we're pulling the samples for the uh, confidence interval?
I didn't hear the full question. I'm sorry.
Whenever we're trying to pull the sample for like a confidence interval,
Mm-hmm.
do we use a statistical method to pull those samples out?
Well,
Or
yes. What you'd want to try to make it as close to a random sample as possible. So let's say that I was interested in students' GPAs or something, and I'm going to try to build a confidence interval. I would want to at least ask the registrar to they've got the list of all the students to kind of randomly generate either in Excel using random number generators or if they have another tool. But yeah, that would be that probability sampling. You want to try to use a probability sampling method, and that's going to include some type of randomness to it. Ideally, if it's something where you've got Excel, like names in Excel, you can use the random number generator and just randomly generate numbers to pick from those.
Mm.
Most statistical programs do have some type of a random generator to them. But yes, that you as much as possible, you want to do random selection. And that would
okay,
be our statistical tool to use, the
okay,
randomness.
thank you.
Yes.
Do you think that like statistics in general have become more accurate as technologies increased, or versus like familiarity with the use of statistics?
I don't think it's gotten more accurate, but I think people have gotten better at using it because it's like this, as you saw with SOFA there, it's pretty easy to use once you get a general idea. I think like when I was in college, now, granted, this was the dark ages, my notepad was a stone and I had to chisel my notes in stone. But, you had all those calculations to do. Truth be told, when I went to college, we didn't even have calculators. They were so new, they were expensive, and teachers would not allow people to use calculators because that gave them an unfair advantage to the rich kids. So we had to do calculations manually. Or if you knew how to use a slide rule, you could use one of those. So I think a lot of people exposed to different tools just focused on that tool and how do I get the answer? They didn't really get to understand. Now that part of it's easy. Getting that, put the data in, you're going to get that p-value, you're going to get that stuff. Now you can focus more on interpreting things and understanding what you're doing. So I think it's not any easy, but I think people have a chance to actually understand it, especially as you use it. You know, as you use it and as you do it, you start to say, oh, now I really get what I'm doing with this hypotheses test.
So Brian, what's the what are the college courses to look for? Is this all going to be covered and have utility in a stats 101, or is this 101 and 102? What are we looking at if we want for more?
Yeah, a lot of places they've gone down to just the stats 101 type course, just simply because we're trying to cut down how long people have to take classes and all that. So yeah, most of this would be covered in a stats 101 type course. Typically, it's all going to be numerical data you're going to analyze. If you take a stats course through like a behavioral science type program, they're going to deal a lot more with qualitative data. We don't, in the courses I teach, we don't do the chi-squared for associations, between categorical data. So some of your behavioral science geared, like psychology statistics. We have a course now at the community college that is stats for psychology. And so it focuses more on the tests that they would do, even though we have a, stats 101 course. You can only cover so much in one semester course,
Sure. That's a good point. There's probably data analysis for healthcare, data analysis for marketing.
Yeah.
For the various domains out there,
Yep.
which uses practical examples, I would think, from those areas. Okay.
Yeah, and they focus on the tools that are most appropriate for the type of data you would collect in those areas.
There you go. Any other questions before we let Brian go for the day?
I have a question.
Yeah.
When do you find it useful to categorize numeric data? Like those age groups,
Yes.
like were bundled, but I assume you could also run a correlation between just the discrete age. So when are you looking at data and thinking like, we need to categorize this data like into groups?
Judgment call on if there's a lot. There was like 1,500 in there, and so having all those individual ages, it's useful, but it was a little bit more useful to be able to kind of group them. And so, yeah, that's what I would say. For me, it's always been a very subjective decision based on what I'm trying to analyze. Now, back when COVID first started, when we started and they were talking about maybe masks, maybe not, I was working for a political campaign. I won't say who or what party, but it wasn't any of the major parties. It was a small party. And so I did a survey about, because I was interested in, was you're wanting to wear a mask voluntarily, did that, was that impacted by your political party that you believed in, what you identified as a Democrat or Republican? And so I also got ages. And so what I was also interested in that age, and that's one of the things I did was I just kind of collapsed the ages a little bit, just because there were just so many of them and it really didn't have any, I looked at it separately, but it just was a lot and it seemed more beneficial to collapse. Some of the tools you use, you will have to collapse. They can't handle a lot of different categories like that. But I always recommend collect, when you're collecting the data, get the best data you can like this, get their age. Don't ask them what their age group is, get their actual age, because then you can always collapse it later on.
So I have a follow-up on that. Is there like a rule of thumb when you're grouping data? Like if, for example, maybe you have 100 people in the 20 to 30 category, but then there's only 5 in the 6. Do you need to group with similar sizes or?
Not necessarily, but if you're working a lot with the chi-squared, for example, you're going to break it down into cells, and each cell, and I don't know the exact numbers off the top of my head, but sometimes the tools, you have to have a certain number in each group for the tool to give you a valid result. So you might do that. You might, that's why I say, my second rule is always check your assumptions of the data and the tool you plan on using, because if you don't have enough, then you may have to collapse, or if you have too much, you may have to break those groups apart a little bit. There are some guidelines, but I would say it depends more on the tool you're going to use to analyze it than any one guideline that applies across the board.
Okay. Anyone else?
I'm really surprised my cat didn't come running over and jump on my computer. Normally, when I try to do office hours or talk to people, he hears the voice and he comes running over.
Yeah, we had the. I was on a meeting yesterday. We had the cat butt in the camera. That's like, all righty.
Yeah.
Brave new world. All right. Well, thanks, Brian. I think this added just the right amount of fidelity to that notion of hypothesis testing and your before and after groups and whatnot. Can you email me those slides?
Yes,
and
yes,
I'll post them for everybody.
Yeah, I just realized when I got on here, I meant to do that to you last night and I forgot.
Okay, cool. And I'll post them in our foundations group.
Mhm.
All right.
All right. Well, thank you very much for this chance to speak to y'all. Appreciate it.
All right. Thanks,
Thank you.
Brian.
Take care.
I'll be in
Thank you.
touch this
Okay.
afternoon.
All right. Have a good one.
All right. Take care. Okay, guys. Another hour or so left in class. I'd like you to continue whichever you were doing, if that was refining your Excel spreadsheet or going through any one of those supplementary tutorials. I would like to see kind of another how you doing and your business question. If you turned it in before and you hadn't added your just your questions, how does this relate to that, or if you could put those in the assignment comments and turn in a new version, that'd be good for me to see. Try and get with the hour and 15 or so here, try and get to a single spreadsheet that that has your, what I started you off with the states and the population, just as an example, and then, but go ahead and finish off your columns. I mean, it really, once you get a data set, it only takes a few minutes. Finish off your columns. If you make progress in charting what you're looking for, that's great too. But finish that off this afternoon and repost it and put in the assignment comments what it is you're trying to address. Because I want to grab those out kind of like I did a couple of them before, and I want to look at some things, whether it's putting it in a pivot table or running these different statistical tests that I'm learning about, so that we can talk about that again on Thursday. And again, as you're going through this, I'll post Brian's slides. If everyone, certainly you don't have all of this experimental design and inferential statistics down in your head 100%. So have a question or two aside for Dr. Worley on Thursday, because at 9 o'clock we're done. I'm not going to put any more stats in front of you or stats expertise. So if there is something at work, like we were just talking about, kind of eyeballs before and after, how to measure, I think it might have been Aaron, it might have been Chase, wanted to measure engaging young readers. How would you measure that? How would you construct that experiment? What would you be looking at? How would you get that data? So be thinking about those sorts of things. And then, like you guys in healthcare, we're looking at coverage and how far willing people are able to drive, when it's time to open up another clinic, how being in an underserved community affects your healthcare. So be thinking about your domain and what we've learned, and we'll make sure it's not just me asking asking stupid questions, but you all need to help shelter me and also ask questions. And okay, so that's the rest of the day, and then we'll do that with Dr. Worley, and then a little bit more with Excel, and a little bit more with Python. And I want to pretty quickly here start working into SQL and working with the database. I've got my my buddy Justin working on your accounts in the Mariah DB that you'll be connecting to with SQL Workbench. Any questions or concerns for me, or what I'm looking for? I want a new version of your spreadsheet, okay? At some point today, before the end of the day. Questions? Going once, twice, three times. Okay, guys. Holler if you need me. Everybody's got my cell. Just shoot me a text if you need me to call you or something. All right, and I'll see everybody Thursday morning at 8:30.
Have a good night.
Have a good one, guys.
Yeah.
Yeah.